Wouldn't it be awesome to run your Python code 35,000 times faster with very small code changes? And yes, you heard it right, 35,000 times faster. This is the promise of Mojo, a new language extending the familiar Python syntax that was unveiled a couple of days ago. But while the speed of execution is important, there are many other features that make me, as a dev and a machine learning engineer, extremely excited about Mojo. So to prepare ourselves for what the future has in stock for us, let us take a look at what Mojo is and what it can do, who are some of the people behind the language, and the secret to its performance lies there, and also at Mojo in action, a live example of using Mojo with a side-by-side comparison versus Python. Let's get started. So what is Mojo? Mojo is a new programming language for AI developers, and it combines the usability of Python with the performance of C. Okay, so what does that mean? Well, we start with the familiar syntax of Python, and then Mojo builds on top of that. So it adds a couple of things that allow us some really cool features and that enable this amazing performance. So when Mojo is mature, what will happen is that it will be able to run all your Python code, and out of the box you will get a much better performance for free. So I think that this is really cool. So let's look at some of Mojo's features. And the claim is write everything in one language. All right, so you will be able to write in Mojo. You are able already to write in Mojo, but then this will get translated to multitude of low-level AI hardware. So we'll go from the high-level programming language that resembles Python to machine language, and it will be runnable on your standard CPUs as well as GPUs. Now, some of the features are progressive types, right? So proper typing will enter the Python world, which can help us avoid bugs, and on certain projects, this can be very helpful, especially those larger scale projects where many developers are involved. Then we have zero cause abstractions. So this is quite amazing because what they say here is take control of storage by inline allocating values into structures. So this is a new data type, which is somewhat like a Python class, but it's not dynamic. So you will not be able to define things on that class at runtime. But what happens is that this allows the compiler to optimize memory allocation so that all the values can be accessed very quickly. And that's one way of attaining massive speedups. The next thing here is ownership and borrow checker. So this is the safety of Mojo. It is claimed to be as safe as Rust, which will be amazing if that happens, and I have no reasons to believe that it won't. So the next thing here is portable parametric algorithms. Right, leverage compile time meta programming to write hardware agnostic algorithms and reduce boilerplate. Meta programming is a double-edged sword, so it's something that gives you a lot of power, but if you're not careful, it can really bite you. But I'm quite a big fan of meta programming. I started to program in Ruby, and it features some wonderful meta programming that I've been missing in Python. So it's awesome that this is coming and will be natively supported in the language that I use nowadays. Now, Python already has some meta programming, and you can change the meta classes, you can do a lot of fun things, but this is still not as fully featured as it will be in Mojo. And the next thing is language integrated auto-tuning. So this is really cool because what this is, essentially you'll be able to write your code, and then Mojo will look at the hardware that you have available, and it will tune the code to the platform that you're running on. So it's a little bit like PyTorch compile, but available across more platforms, which is Again, something that I'm quite looking forward to. So how come all these wonderful features? Well, in large part due to this gentleman right here, Chris Lattner, who is quite famous for giving us the LLVM. So LLVM is a component that helps take the code that you write in a language such as C++ or Ruby or Scala, even in Python, and it translates it to machine executable code. So it's a key component in that operation, and really a lot of what we take for granted in the modern programming world leverages LLVM. So we have C++, we have C, we have Objective-C, Python as well, I believe, but not the entirety of Python. So if you use Numba, it will let you use a subset of Python, and that will get compiled using LLVM, Scala, Rust, and many more languages. So, this is a really ubiquitous tool. But the next step in the evolution of LLVM is MLAR, and that's something that Chris Lattner was also involved in, and by involved I mean that he helped lead the effort at Google. So MLIR takes the LLVM idea to the next level and makes it even more flexible, and brings those ideas to the world of AI programming. So TensorFlow and allows the AI goodness to be more natively supported. One other thing worth mentioning is that Chris Lattner led the Swift team at Apple, and Swift already had a lot of exciting ideas, and it was a great, I would imagine, training ground for someone like Chris in developing a language that would be very widespread, that would have great usability, and that would out of the box support very good performance and very interesting features. So it is not a far-fetched idea that working at a startup such as Modular, Chris might have an even better opportunity to implement some of his ideas and take them to the next level. But apart from Chris, there are many good people involved with Modular. Some of the people I know personally, and they're amazing talent. So I'm excited for what comes next, for the future releases. Okay, so let's take Mojo for a spin. This is an environment that is created by the Modular team. It's the playground, and it's a multi-tenant environment. So unfortunately, the code that we will run here will run on some AWS instance that is possibly shared with other people executing the notebooks, but this still will give us a good understanding of what the performance roughly looks like as compared to Python. It will not be exact, it will not be precise, but we're more of looking at the order of magnitude of things here than getting an exact answer. So Mojo, we are running in a kernel that in a Mojo kernel, and we can see that we can run Python code inside of Mojo. We can also import libraries, Python libraries, into Mojo. So let's see, here we will be looking at matrix multiplication, which is a very fundamental operation to anything that we do in machine learning. And let's see how fast that operation runs on a CPU using Python. So we get some performance right here. All right, and let's see how that compares to executing essentially the same code, but running Mojo. So we import a couple of Mojo libraries, and here we define the matmul operation. And now, since we will be running this in Mojo, and Mojo doesn't have certain things just yet or have things organized differently, For instance, it doesn't have the timed module that we used above. So some of the things had to be slightly reorganized, but as you can see, the syntax is very familiar. It all looks like Python. It is the syntax of Python. And the key component here, which is the inner loop, which is where most of the execution time goes to, is essentially the same. So let's run this code now. We define the functionality, and we now can benchmark the performance against Python. So let's see what result we get here. And all right, so it's a 17x speed up versus Python. So this is amazing, because essentially this just shows you that you will be able to take your Python code and plop it into Mojo. And ideally, when Mojo is mature and has all the planned functionality, you will be able to execute your code much faster. Also, the nice thing here is that Mojo allows you to import libraries, Python libraries, and seamlessly integrate them with your Mojo code. So you can imagine that you will be able to import numpy or pandas. But the very interesting thing here, the promise of Mojo, is that maybe some of these libraries will be getting rewritten in Mojo, or there will be new libraries that will be written in Mojo natively. And this unlocks even on a single CPU core, even without using types. So we're still in the dynamic programming setting here. You know, this already gives you a nearly 20x speed up. But let's keep going. Let's see what else we can do here. Okay, so now we will define the operation and perform it on the same data, but we will add type declarations. So these things right here, they are type declarations, and they tell the compiler what will live in a particular variable. And this is a super valuable hint to the compiler, because it allows it to do a lot of optimizations. So let's take a look how quickly the code will run now. Okay, just defining some functionality, and let's run the code. So I'm running the code right now. Okay, so it's nearly 2000x speed up. And whenever you're using a dynamic programming language such as Python or Ruby or any other scripting language, you are paying the price for the convenience of not having to define types, for the maybe number of lines that you have to write, number of lines of code, because generally code without type declarations is shorter. Is maybe also a little bit more friendly for the reader, but you pay the price in performance, because the execution cannot be optimized as well. And as we can see, the price can be very high. Okay, so we've already sped up the operation by 1800 times, but what else does Mojo has in store for us? Vectorizing the innermost loop. Right, so we will be able to leverage the SIMD instruction set. This is something that your CPU supports, and this is just a way to execute certain operations much faster, make better use of memory again, and just run things at much higher speeds. And let's see. So this gives us a further 3x improvement, and we're now running nearly 7,000 times faster than our code ran in Python. So that is quite spectacular, but hey, no one likes to vectorize things by hand. At least I'm not the biggest fan of that. So let's now see how will the same code performed when we vectorize it using a functionality that comes with Mojo. And we see that we get exactly the same performance. So that's quite nice. But now the fun thing is, it's so very hard to run things on multiple cores in Python. and our machines, even a laptop nowadays, has 8, maybe 12 or 16 cores. Server CPUs also have many cores, and so often, and that goes for any project that I would work on, be that a Kaggle competition, or maybe back in my previous life working on customer projects and doing something for a customer. Very often I will come across this vast amount of data, and even basic processing like resizing an image, that can take forever. And by forever, I mean if we have 500,000 images, that's where the forever comes from, because individually processing each image is fast, but given the size of the data, that can be very, very taxing and can take a lot of time. So naturally, you want to use as many cores as you can. And in Python, that operation unfortunately requires that you write specialized code, and leveraging those multiple cores is not fun, not resource efficient, because you still have to think about memory access and things like that. So being able to completely remove that consideration altogether would be wonderful. But let's see how does that work here in Mojo. So we just parallelize the operation and we get further speed up. And this is something that I'm extremely excited about, because this is the level of complexity that I want when parallelizing my code. I don't want to be thinking about so many things that you have to think about, like race conditions, like the overhead that you incur in terms of memory, and the communication aspect of things that for certain applications that you have to also take into account. And here the compiler figures all that out for us, and we get very good performance again. So we're now 28,000 faster than the code implemented in Python. But we can do more. So we can tile the matmul operation. And what does that mean? Well, tiling deals again with memory access, how things are organized in memory, and it can figure out what architecture you are running on, and it can improve the execution again. So let's rerun this again. I'm in a multi-tenant environment, as I stated earlier, so those results might not be telling. Assuming everything goes well, we should be getting a further speed up on top of the performance before. Okay, so maybe someone is on the same VM and is executing their code as I record this video. But through organizing the data better in memory, through taking advantage of the hardware platform that you're running on, you should get an incremental speed up on top of the parallelized version. We're sort of seeing it here, but the effect is maybe a little bit smaller than we could expect. Still, it will not be revolutionary, but you will squeeze additional ounces of performance using tiling. And what else do we have here? Right, so this is further optimization. We can unroll some of the loops introduced by Vectorize, and we gain another speed up with very few code changes. Essentially, we just import a different function from Mojo, and that does the magic for us in the background. Now, there's another thing that can be optimized here, and that's the tile factor, which defines how the operation of tiling is performed. So we can auto-tune it to the hardware platform that we're using. And let's see here. Okay, so previously we were just tiling in a way that is platform agnostic, and only here do we auto-tune the execution to the platform that we're on. Again, we're on a multi-tenant platform, so maybe we'll not see a speed up as high as we would otherwise, but yes, we're roughly in the same ballpark, and we probably can only expect an incremental improvement here. So the promise was that we would reach 35,000x improvement. On this particular hardware, we reached a 29,000x improvement with having to write little extra code, essentially relying on the functionality that Mojo provides out of the box. Mojo is not out yet, but I expect regular releases over the weeks and months to come. So now that we have this awesome language to implement things in that can run very fast, you know what's really cool? Having something fabulous to actually implement in that language. And for that, as a source of inspiration, nothing works better than academic papers. So if you'd like to learn a little bit more about how to read academic papers, regardless if you have an academic background or not, I myself don't even have a college degree, do check out the video that I recorded a couple of days ago. Thanks for watching. See you around.